Welcome to today's paper reading. Today's paper is titled, GNN-RAG, Graph Neural Retrieval for Large Language Model Reasoning. This paper, authored by Costas, Mavromatis, and George Karypis from the University of Minnesota, introduces GNN-RAG, a novel method for combining the language understanding abilities of large language models, LLMs, with the reasoning abilities of graph neural networks, GNNs, in a retrieval-augmented generation, RAG, style. The work is currently under review. This work introduces GNN-RAG, a novel method that combines the language understanding capabilities of large language models, LLMs, with the reasoning abilities of graph neural networks, GNNs, for knowledge graph question answering, KGQA. Knowledge graphs, KGs, are structured representations of factual knowledge using triplets, which form a graph. LLMs are currently the state-of-the-art for question-answering tasks due to their strong natural language understanding. GNNs, on the other hand, are effective for KGQA as they can process the complex graph information stored in KGs. GNN-RAG employs a GNN to reason over a dense KG subgraph to retrieve answer candidates, and then uses the shortest paths connecting question entities and answer candidates to represent KG reasoning paths. These paths are verbalized and input into the LLM for further reasoning in a retrieval-augmented generation (RAG) style. Additionally, a retrieval augmentation technique is developed to enhance KGQA performance. Experimental results demonstrate that GNN-RAG achieves state-of-the-art performance in 2 KGQA benchmarks, outperforming or matching GPT-4 performance with a 7B-tuned LLM, especially excelling in multi-hop and multi-entity questions. Large language models, LLMs, are currently the leading models in various natural language processing, NLP, tasks due to their exceptional ability to comprehend natural language. These models derive their power from being pre-trained on extensive corpora of textual data, which allows them to acquire general human knowledge. However, the process of pre-training is both costly and time-consuming, making it difficult for LLMs to adapt to new or domain-specific knowledge and prone to generating hallucinations. Knowledge graphs, KGs, on the other hand, are databases that store information in a structured form, making it easy to update. They represent human-crafted factual knowledge in the form of triplets, which collectively form a graph. KGs are widely used in knowledge-intensive tasks such as question answering, QA. Retrieval-augmented generation, RAG, is a framework designed to mitigate LLM hallucinations by enhancing the input context with up-to-date and accurate information, often obtained from a KG. This approach is crucial for tasks like KGQA, where the goal is to answer natural language questions by grounding the reasoning on the information provided by the KG. Figure 1 illustrates the performance comparison on multi-hop and multi-entity KGQA tasks. The GNN-RAG method significantly outperforms existing KG-RAG methods, achieving an F1 score improvement of 8.9 to 15.5% points. Specifically, the F1 score for the no-RAG approach is 70.2%, while GNN-RAG achieves a notable 77.2% F1 score, demonstrating its effectiveness in handling complex KGQA tasks. In the field of knowledge graph question answering, KGQA, methods can be broadly categorized into semantic parsing, SP, and information retrieval, IR. SP methods aim to convert questions into logical forms, such as SPRQL queries, which are then executed on the KG to retrieve answers. However, these methods require annotated logical queries for training, which can be time-consuming and may result in non-executable queries due to errors. On the other hand, IR methods operate in a weakly supervised setting, where only question-answer pairs are used for training. These methods focus on retrieving KG information, such as subgraphs, which serve as input for KGQA reasoning. Additionally, recent advancements include GNN-based and LLM-based methods, which leverage the strengths of graph neural networks and large language models, respectively, for enhanced KGQA performance. Figure 2 illustrates the landscape of existing knowledge graph question answering, KGQA, methods. GNN-based methods, such as GraphNet and NSM, reason over dense subgraphs, leveraging the GNN's capability to manage complex, multi-hop graph information. In contrast, LLM-based methods, like TOG and RAG, utilize the same LLM for both retrieval and reasoning tasks due to the LLM's proficiency in natural language understanding. The figure highlights how GNN-RAG integrates the strengths of both GNNs and LLMs to enhance KGQA performance. The task of KGQA involves extracting a set of entities, A, from a knowledge graph G that correctly answer a natural language question Q. Given G and Q, the goal is to find the relevant entities without the ground truth paths that lead to the answers. For retrieval and reasoning, a smaller question-specific subgraph GQ is retrieved from G, which ideally contains all correct answers. This subgraph, along with the question, is then used as input to a reasoning model, which can be either a graph neural network, GNN, or a large language model, LLM. GNNs classify KG entities as answers or non-answers, while LLMs perform retrieval-augmented generation, RAG, by converting the subgraph into natural language for processing. The landscape of KGQA methods includes both GNN-based and LLM-based approaches, each with its own strengths in handling complex graph information or leveraging the power of LLMs for retrieval and reasoning. The GNN-RAG framework combines the language understanding of LLMs with the reasoning abilities of GNNs. The GNN processes a dense KG subgraph to retrieve potential answers and extracts the shortest paths connecting the question entities to these answers. These paths are then verbalized and provided as input to the LLM for further reasoning. The GNN updates are performed L times, with nodes scored based on their final representations. During inference, nodes with high probability scores are considered candidate answers. The LLM, such as Llama 2 Chat 7b, is fine-tuned using prompt tuning techniques to generate accurate answers based on the reasoning paths provided. Figure 3 illustrates the GNN-RAG framework, which combines the strengths of GNNs and LLMs for knowledge graph question answering, KGQA. The GNN processes a dense subgraph to identify potential answers and the shortest paths connecting the question entities to these answers. These paths are then verbalized and fed into an LLM, which uses them to generate responses in a retrieval-augmented generation, RAG style. This approach leverages the GNN's ability to handle complex graph interactions and the LLM's natural language processing capabilities to enhance KGQA performance. Table 1 presents the retrieval results for the WebQSP dataset, comparing the performance of deep GNNs, L equals 3, and shallow GNNs, L equals 1, against an LLM-based retriever. The results show that deep GNNs are more effective and efficient in handling complex graph structures and retrieving multi-hop information. However, for simple one-hop questions, the LLM retriever performs better due to its superior natural language understanding capabilities. In this experimental setup, we utilize two key datasets for KGQA, Web Questions SP, WebQSP, and Complex Web Questions, CWQ. WebQSP consists of 4,737 questions requiring up to 2-hop reasoning, while CWQ includes 34,699 questions with up to 4-hop reasoning. For implementation, we employ the PageRank algorithm for subgraph retrieval and use RayRev combined with SPERT for GNN-RAG. Evaluation metrics include hits at 1, H at 1, and F1 score. We compare our methods against state-of-the-art GNN and LLM methods, as well as earlier embedding-based and zero-shot/few-shot LLMs. Table 2 presents a performance comparison of various methods on two knowledge graph question answering, KGQA, benchmarks. The table highlights that GNN-RAG plus RA achieves superior results, outperforming RAG by 5.0 to 6.1 percentage points in hit metrics. This method also matches the performance of TOG plus GPT-4, despite using an LLM with only 7B parameters. Additionally, GNN-RAG plus RA surpasses TOG plus ChatGPT by up to 14.5 percentage points in hit, and it outperforms the best-performing GNN by 5.3 to 9.5 percentage points in hits at 1 and by 0.7 to 10.7 percentage points in F1 metrics. Table 3 presents the performance analysis of various methods on multi-hop and multi-entity questions in the context of knowledge graph question answering, KGQA. The table highlights that GNN-RAG, a method leveraging graph neural networks, GNNs, significantly outperforms RAG, an LLM-based retrieval approach, by 6.5 to 17.2% in F1 score on the WebQSB benchmark. Additionally, GNN-RAG plus RA, an enhanced version of GNN-RAG, shows further improvements, achieving an F1 score increase of 8.5 to 8.9% on the CWQ benchmark. Notably, GNN-RAG plus RA achieves impressive F1 scores of 82.3 to 88.8% on multi-entity questions in WebQSB, demonstrating its effectiveness in handling complex graph information and multiple question entities. In this section, we present the main results of our study. GNN-RAG has demonstrated superior performance as the best overall KGQA method, achieving state-of-the-art results on two major benchmarks. Specifically, it outperforms the RAG method by 5.0 to 6.1 percentage points in the hit metric. Additionally, in multi-hop and multi-entity KGQA tasks, GNN-RAG significantly outperforms RAG, showing improvements of 6.5 to 17.2 percentage points in the F1 metric. This indicates its effectiveness in handling complex graph information. Furthermore, our analysis of retrieval augmentation reveals that GNN-based retrieval is more efficient and effective than LLM-based retrieval, especially for complex questions. The best performance is achieved when combining GNN-induced and LLM-induced reasoning paths, which fetch non-overlapping KG information. However, augmenting all retrieval approaches does not necessarily improve performance due to potential LLM confusion from long inputs. Table 4 presents a performance comparison of different retrieval augmentations for GNN-RAG in the context of knowledge graph question answering, KGQA. The primary metric used is F1 score, which measures the effectiveness of retrieval methods. The table highlights that GNN-RAG, which leverages graph neural networks, GNNs, to handle complex graph information, significantly outperforms LLM-based retrieval methods, particularly on complex questions from the CWU dataset. Specifically, GNN-RAG achieves improvements of 6.5 to 17.2% points in F1 score on the WebQSB dataset and 8.5 to 8.9% points on the CWQ dataset. Additionally, the use of retrieval augmentation, RA, further enhances performance, with GNN-RAG plus RA showing improvements of up to 6.5% points in F1 score. The results indicate that combining GNN-induced reasoning paths with LLM-induced reasoning paths can fetch non-overlapping KG information, thereby improving retrieval accuracy for KGQA tasks. Table 5 illustrates the impact of different retrieval methods on the performance, % hit, of various LLMs. The data shows that GNN-RAG with retrieval augmentation, GNN-RAG plus RA, significantly enhances the performance of LLMs like ChatGPT, improving its hit rate by up to 6.5 percentage points compared to other retrieval methods like RAG and TOG. Additionally, GNN-RAG demonstrates superior performance over Llama 2 Chat 70B when paired with a lightweight 7B model. Notably, GNN-RAG also substantially boosts the performance of weaker LLMs such as Alpaca 7B and Flan T5XL, with improvements of up to 13.2 percentage points in the hit metric. This table underscores the effectiveness of GNN-RAG in enhancing KGQA reasoning across different LLMs without the need for retraining. Figure 4 presents two case studies demonstrating how GNN-RAG enhances the faithfulness of LLM responses. In both scenarios, GNN-RAG successfully retrieves multi-hop information essential for accurately answering complex questions. This improvement is crucial for ensuring that the LLM adheres to the question's instructions and utilizes the correct information from the knowledge graph. Specifically, in the first case, GNN-RAG fetches both critical facts required to answer the question, unlike the baseline KGRAG which only retrieves the first fact. In the second case, GNN-RAG correctly identifies the necessary entity type, whereas the baseline incorrectly retrieves irrelevant information. These examples highlight GNN-RAG's ability to enhance LLM performance by ensuring the retrieval of accurate and relevant multi-hop information. Figure 5 demonstrates a case study highlighting the advantage of retrieval augmentation, RA, in enhancing the performance of GNN-RAG. RA leverages LLMs to retrieve semantically relevant knowledge graph, KG, information that the GNN might overlook. This additional information is crucial for the LLM to accurately answer the question. The case study shows how RA fills in the gaps left by the GNN, ensuring that the LLM has the necessary context to provide correct responses. In this study, the authors introduced GNN-RAG, a novel method that combines the reasoning abilities of large language models, LLMs, and graph neural networks, GNNs, for knowledge graph question answering, KGQA. The framework of GNN-RAG repurposes GNNs for KGQA retrieval to enhance the reasoning capabilities of LLMs. Additionally, the retrieval analysis conducted by the authors guides the design of a retrieval augmentation technique to boost the performance of GNN-RAG. The method demonstrates state-of-the-art performance in two widely used KGQA benchmarks, WebQSB and CWQ. It is also shown to retrieve multi-hop information that is essential for faithful LLM reasoning on complex questions. In terms of efficiency, GNN-RAG improves KGQA performance without the need for additional LLM calls, a requirement in existing RAG systems for KGQA. Furthermore, GNN-RAG either outperforms or matches the performance of GPT-4 using a 7 billion parameter tuned LLM. Thank you for watching.